Hey guys, today we are starting our introduction to calculus. So first thing to start off with are something called limits. Now before we actually get to talking about what a limit is, let's talk about what it means to be continuous. So a function is continuous if it can be drawn without lifting up your pencil. There's no breaks or gaps or anything like that. So there are three different types of discontinuity. There's a point discontinuity, which is called a hole, and it's literally one point is pulled out of that function. An infinite discontinuity is when we have an asymptote. So we've seen point and infinite discontinuity in rational functions. Remember, if we had the same thing cancel out on top and bottom, when we set that guy equal to 0, we get an x value, we would have a hole there. Whatever was in the denominator left over gave you your vertical asymptotes. The other type of discontinuity is going to be piecewise or step functions. Those are, piecewise are, when you have one piece of a graph over here and then another graph over here, it kind of does a little jump in between. And then step functions, we'll look at the ceiling function here in just a moment. So we want to find out for what values is f discontinuous, and then describe the type of discontinuity. So what might be helpful is to go ahead and look at this in a graph. So I'm going to go ahead and open up Desmos. And remember, we're looking at 3 sine of x. So if we take a look at this function, it's just going to keep on going and going and going and going. And we could keep on graphing that with our pencil without having to pick it up, right? So that means, where is it discontinuous? Nowhere. F is continuous. Good deal. Now we're going to look at the ceiling function. Good deal. So this is a step function. You notice it looks like steps. So where is it discontinuous? Well, if we take a closer look here, I have breaks at 1, at 0, 1, 2, 3, all the way up, right? So I'm discontinuous at every integer. So where is it discontinuous? Where x is an integer. Now, to get from one value to the next, we have to kind of jump up to the next value, jump up to the next value. So that's why that's called a jump discontinuity. Good deal. Now let's take a look at this guy. So he's a rational function. Remember, that's where we have holes, asymptotes, things like that. Okay. Now, here, we can see obviously that we have a discontinuity right here happening at, let's see, it must be -3. At -3. So this is discontinuous at x equals -3. Since my graph is going in two different ways there, I actually have an asymptote there. So since there's an asymptote, that means it's an infinite discontinuity. Now, there's actually another discontinuity in there as well. So let's go ahead and bring him back in. If we were to follow along here, when we get to, oopsies, not -5, +5. Over here at +5, we're undefined there, right? So we actually have a point discontinuity. If I can move my, oh, nope, it won't let me. If I get right back on there, we can see that there's faintly a little circle. There's a hole there. So here's how we can find that out algebraically. So real quick, at x equals 5, we have point discontinuity because we have a hole. So here's how we can figure this out without having a graph because, right, we can't really see holes there, right? So what we can do, we already have that x minus 5 on top, over, and then we can factor our denominator. Two numbers that multiply to -15 and add to 2. That's going to be x plus 3, x minus 5. So since this x minus 5 piece would have canceled out, that's where our hole is. So we would have set x minus 5 equal to 0, and then we have that hole at x equals 5. Over here, we can't divide by 0, so after that x minus 5 cancels out, we're left with that x plus 3, and we'll set him equal to 0. And that means we have an asymptote there at -3. Okay, so now that we know what discontinuities are, let's talk about a limit. So a limit is the best prediction of a point that we didn't observe. So the best way to make a prediction is to zoom into the neighboring points and see where is my graph going. Now, here's the thing. What the limit is doesn't actually have to be the value of that graph. So, for instance, if we were to plug in 5 into this equation, we would have 0 divided by 0. That's undefined, right? And we had a hole there. But we can see that at values really, really close to 5, we're approaching the same thing there. So actually, it doesn't matter what the value is at 5. We're looking at everything getting closer and closer and closer to 5. So we're just assuming that we don't know what the value is when I plug in 5. But I'm going to look at everything else close to it to make a guess. So since I'm looking at everything else close to it to make a guess, both my left-handed limits and right-handed limits have to match. So here we go. What we're going to do is we're going to look at a table of values that are very, very close to x. That always works. And then we can also substitute x into a function to see if it's defined. And then also we're going to look at a graph. So we're going to find the limit by using a table of values here. So we want to find the limit as x approaches 3 of 4x squared plus 7. So let's go ahead and open up our calculator. Okay, so you want to press second and then window to get to table set. Have your independent set to ask, so that way you can enter in values for x. And have your dependent on auto, it will give you all those values back. So we're going to go to y equals, and we're going to put in our function of 4x squared plus 7. And then we're going to go to table. So second graph to get to table. All right, these aren't the values we want. Hang on just 1 minute. Okay, so the left-handed limit. So this will be the limit as x approaches 3 from the left. We have a little negative sign up there with the 3. That means I'm coming from the left side of my graph of 4x squared plus 7. So from the left, those values getting closer to 3 are going to be like 2.8, 2.9, 2.99. So that's what we're going to plug in now. I'm going to type in 2.8. Enter. 2.9. Enter. 2.99. Enter. We can see that we're just getting closer and closer and closer to, well, maybe we should do 2.999 and see what that is. We're just getting closer and closer and closer. We're at 38, then 40, then 42.7, then 42.9. We're getting closer and closer and closer to about 43. Now let's look at the right-handed limits. So the right-handed limits are going to be the ones that are just larger than 3. So our right-handed limits, the way we write that, is a limit as x approaches 3. From the right, we're going to have a little plus sign up in the corner of 4x squared plus 7. So we're looking at values just to the right of 3. So we're going to think of things getting just a little bit bigger. So there's 3.1. A little bit closer to 3 is 3.01. Oopsies, that's not right. 3.1. 3.01. There we go. 3.001. So once again, we got 45, 43.24, 43.024. So each time we're getting closer and closer and closer to about the value of 43. So as we can see here, my left-handed limit and my right-handed limit here are the same. They're both 43. So that means the limit as x approaches 3 of this guy, oopsies, is 43. Now, like I said, looking at a table of values always works. But another way we could have done this is just plug in x into the function. So if we were to plug in 4 times 3 squared plus 7, 3 squared is 9, times 4 is 26, or is 36, plus 7 is 43. But we're not always able to just plug in a value. So if we were to plug in 4 to this guy, we would end up with 0 over 0, and that's undefined. So we can't just plug in the value for x. So we need to look and see what's going on at each side. So we're going to look at our left-handed limit, the limit as x approaches 4 from the left. So we have that little negative sign of, and I'm just going to call this f of x so that way I don't have to keep writing out that function because that's kind of gross. Okay, so we're going to go to our y equals. We're going to clear that guy out. Let's see, our numerator is x squared minus 6x plus 8. We'll divide that by our denominator of x squared minus 2x minus 8. Close this parentheses. And we'll go back to our table. All of these values are from earlier, so I'm just going to clear guy. Okay, I'm just going to type over it actually. Okay, so I want to look at values that are to the left of 4, so a little bit less than 4. So that value might be 3.9. A little bit closer to 4 is 3.99. A little bit closer to 4 is 3.999. So we're getting 3.22, and then we're getting 0.322, and then 0.332222, then 0.333222. So every time we're getting a little bit closer to 1/3, or 0.3 repeating. Then we'll look at our right-handed limit. Limit it as x approaches 4 from the right, so we have a little plus sign up in the corner of that function f of x. So now we're going to plug in things that are a little bit bigger than 4. Oopsies, wrong window. So now I'll be plugging in 4.1. A little bit closer is 4.01. A little bit closer is 4.001, and so on and so forth. And we can see here we have 0.344, 0.3344, 0.33444. So we're getting closer and closer. Oopsies, I didn't put the extra 0 in. We're getting closer and closer and closer to 0.3. Repeating. Or 1/3. Now, if we actually plug in 4, it says error. We're undefined there, right? So what's happening is we actually have a hole there at 4. From both sides, my graph is approaching 1/3. But at 4, I just don't have a value there. But we don't actually care what's happening at 4. We just care what's happening around it. So just to double check this, let's take a look at the graph. Okay, so with our graph, we can see that right here, we're getting 1, 2, 3, 4. Here's about 4. We can see that we're right about at 1/3. Now, once again, if we were to plug in -2 into this equation, we would get 4 divided by 0, and that is not okay. That's undefined. So we are going to look at each side. Our left-handed limit, the limit as x approaches -2 from the left. I'm going to keep on calling this f of x. So let's go to our calculator, go to y equals, and clear out what we have in there. And now we have 4 divided by x plus 2. Yep. So I'm going to go into table. I want to look at things that are to the left of -2, or just a little bit less than -2. A little bit less than -2 means it's going to be, the absolute value is going to be a little bit more. Do you see what I'm saying? So like -2.1 is going to be to the left of -2, since it's less than -2. Okay. And -2.01. And then -2.001. We're just going to get closer and closer and closer to -2. So if we see here, we're going from -40 to -400 to -4,000. Then we'll have -40,000, -400,000. Every time we're getting closer and closer and closer to 2, we're just getting super, super, super negative. So what we're actually approaching there is -infinity. Now let's look at the right-handed limit. So we have the limit as x approaches -2 from the right of f of x. So now we're going to plug in values that are a little bit bigger than -2. So there he is. We're going to plug in stuff that's a little bit bigger than -2. So -1.9. And then -1.99. -1.999. So here we're going from +40 to +400, +4,000. Then it would be +40,000, +400,000, so on and so forth, right? So we're getting bigger and bigger and bigger. But this time, instead of approaching negative infinity, we're approaching positive infinity. You see how my two left-handed and right-handed limits don't match? Since they don't match, that means that the limit does not exist. Now, if you've seen Mean Girls, you have that whole, the limit does not exist moment. Here it is. If the left-handed limit and the right-handed limit don't approach the same thing, that means that the limit does not exist. And what we usually put is DNE for does not exist. Good deal. So now we're going to use the graph of f to answer the following questions. Okay, I'm going to move myself over. There we go. So we're going to look at the graph of f to answer the following questions. What's the domain of f? So remember, our domain is all of our x values. So we start off here at -9, but we have an open circle, so that means we need to have a parenthesis with that -9. Then we have all the values all the way to -5. That's an open circle, but then we have a closed circle right below it, so we're still defined for x equals -5. Then where we run into issues again is here at -2. We have an asymptote there, so that means that I'm going all the way up until -2, but not including it, so we should have a parenthesis. And then we'll have union. We're picking up real close to -2, but not touching him, so we still have that parenthesis. And then we've got values for x until we get to 0. We have an open circle, but a closed circle right above him, so we're still defined at x equals 0. Still have values, still have values, still have values until we get to x equals 4. We have an open circle, but he's filled in down here, so we still are defined for x equals 4. We have a hole right here in our graph at 5, but he's filled in down here, so he's still defined, so he's still part of our domain. And then we have values all the way here until 9. And since we have a closed circle there, that means we include 9, so we should have a square bracket on there. Now we want to find the value of f of -5 and f of 5. So f of -5 is really asking, when x is equal to -5, what's the y value? So right here, f of -5, what's our y value when x is equal to -5? All right, here, it's equal to 3. Then we're going to look at f of 5. So f of 5 says, what's my value when x is equal to 5? Well, x is equal to 5 right here. And there's a circle there, there's a hole there, but it's actually defined down here at -2. So f of 5 is equal to -2. Now we want to see, is f continuous at -5, and why not? So over here at x equals -5, is it continuous there? No, remember, continuous means that we can graph it without picking up our pencil. So we have to pick up our pencil there. So is it continuous? No. We have to pick up our pencil. Now, since we went from one value to the next, there's kind of a hop there. That's a jump discontinuity. And is f continuous at 5? Well, right here at 5, we have a little gap in our graph. So if we were to draw it, we'd have to kind of pick up our pencil, go to the other side, right? And then put a little dot down there at the bottom. So we have something taken out. So is it continuous at x equals -5? No, because there's a hole there. And remember, that's called point discontinuity. Now let's talk about what type of discontinuity happens at -2. So for at -2, we have an asymptote right there. If you can see that red line. And my graph is getting closer and closer on each side and approaching -infinity. So since graphs tend to approach negative or positive infinity at an asymptote, when we have an asymptote, that is called infinite discontinuity. Cool. So now we want to find the limit as x approaches 2 of f. So let's think about it this way. We're also going to have to make sure that the limit as x approaches 2 from the left and the limit as x approaches 2 from the right, we have to make sure that those are the same. So let's go and look at 2. X equals 2 is right here. When we're coming from x equals 2 from the left, we're getting closer and closer and closer to 6. So my left-handed limit here is equal to 6. Now we're going to approach 2 from the right. So coming in from the right, I'm getting closer and closer and closer to the y value of 6. So my right-handed limit is also 6. Since my left-handed limit and my right-handed limit match, that means that my limit exists, and it's this value right here, 6. Now let's look at f of 5. So as x approaches 5, x approaches 5. So the limit as x approaches 5 from the left, and the limit as x approaches 5 from the right. So I'll have a little plus sign there. So let's take a look. Here is x equals 5. So as we're coming in from the left, my graph is getting closer and closer and closer to the y value of 1. Remember, I don't actually care what's happening at 5. I care what's happening around 5. So my graph, really close to 5, is getting closer and closer to 1. From the right side over here, as we're coming in, my graph is getting closer and closer and closer to the y value of 1. So on the right side, my right-handed limit is also equal to 1. So since we're going to the same thing on both sides, that means that my limit does exist, and it's equal to that value of 1. Remember, we don't care what's happening at 5. We care what my graph is going to around 5. Okay, now let's talk about x approaches -2. Now, this one you could have 2 different answers for and still be right. I'm bringing it up just so we can talk about it. So if we look at the limit as x approaches -2 from the left, coming in from -2 from the left, we're just going farther and farther and farther and farther negative, right? So on that side, we're actually getting closer to -infinity. If we look at the limit as x approaches -2 from the right of f, over on this side, we're getting closer and closer to -2, so we're approaching -infinity. Now, some camps will say, hey, your left-handed and right-handed limits match. That means that the limit is going to be -infinity. Others say they can't be approaching the same value because negative infinity isn't actually a number. It's just an idea. So other people say that it doesn't exist. It's the nerd wars. That's what Mr. Atchison calls it. So you could say negative infinity. You could say it doesn't exist. Either way, you'd be right. I'm not bringing it up on anything, though, and you won't see it. I just wanted to make sure that we are well aware. Now let's look at the limit as x approaches 0. So we'll look at it from the left side, the limit as x approaches 0 from the left. So from the left side, I'm coming in and I'm approaching this y value of 3. So from the left, my limit is going to be 3. Now I'll look at my limit as x approaches 0 from the right. So coming in from the right, x equals 0. I'm getting closer and closer to 4. So here, my left-handed limit and my right-handed limit, they don't match. Since they don't match, that means that the limit does not exist. Does not exist. DNE. So your practice today is going to be on delta math. So I went ahead and we're going to try some of these guys so that way you know what you're in for. So we want to enter x values into the table to determine the function values and then use it to answer the questions below. So we want to look at the limit as x approaches -3 from the left. So values that are to the left of -3. So maybe -3.1. Try value. -3.01. A little bit closer. -3.001, a little bit closer. And we can see that each time we're putting that value in, we're getting closer and closer and closer to -3 for my y value. Now let's look at it from the right. So now we're looking at things that are a little bit bigger than -3. So maybe -2.9. Oopsies, that's not where I wanted to put that. I'm going to clear my table. So maybe I want to look at -2.9. Try value. -2.99, a little bit closer. -2.999, a little bit closer. And we can see that we are approaching 6 on both sides. So that's going to be 6. Now, we want to know what's the limit as x approaches -3. Well, they don't approach the same thing on both sides, so that means that my limit doesn't exist. So I'm going to press does not exist. They also want to know f of 3. What is my actual value at 3? Or at -3, I'm sorry. So I'm going to go ahead and put in -3. Try value. And it says -3. Yay, look at us go. Okay, look at, and it'll give you a little explanation of how it works if you need some help. Same idea is going on here. We're looking at from -3 on the left side. So that would be like -3.1, -3.01, -3.001, throw in another 0. It feels like we're just getting closer and closer and closer to -0.6. Now we'll look at it from the right. So we'll try -2.9, -2.99, -2.999, and so on and so forth. And it looks like we're getting closer and closer and closer to -4. Since my left-handed limits and right-handed limits don't match, that means that my limit doesn't exist. And then I'm going to go ahead and enter -3 to find out what the value of my function is there. We'll have -4. Got it correct, and it will explain how that works. Now we want to look at one-sided limits using a graph. So we want to determine the limit as x approaches 3 from the left. So here is x equals 3. Coming from the left, my y value, I'm getting closer and closer to 4. Yay. And then you'll click new problem and keep on going. Okay, so we want to answer all of the questions about this function when x equals 5. So we're looking right here at x equals 5. So the limit as x approaches 5 from the left. So coming from the left, my y value gets closer and closer and closer to -3 there. Looking at the limit as x approaches 5 from the right, so coming from the right, my graph is getting closer and closer and closer to the value of -3. Since my left-handed limit and right-handed limits match, my limit at 5 is going to have to be that value, -3. But f of 5, we actually say if x is equal to 5, what's y equal to? -4. And then it will go through and explain. It even has a little animated graph. I thought that was super nifty, so it's on there for you. Okay. So now it's just straight up asking us, what's the limit at -3? Well, at -3 here, coming in from the left, we're getting closer and closer to -4. Coming in from the right, we're getting closer and closer to -4. Now, actually defined at -3, we're not defined at -3, but nobody cares. We're worried about where we're going. That's -4. And then it will go through and explain. All right. So your assignment is to do the Delta Math practice. That is just like this. If you have any questions for me, make sure you ask. See you guys later.